landscape ecologist with the Aldo Leopold Wilderness Research Institute, which is the only federal research group dedicated to research on wilderness parks and protected areas. It's up in Montana at the University of Montana, and is sort of administered under the Rocky Mountain Research Station of the Forest Service, but it engages managers and researchers from all the land management agencies. Sean has been at the Leopold Center Institute since 2008, where he's actively investigating the relationship between landscape-scale fire patterns and topography, past wildfire, climate, vegetation, and wilderness areas. Sean has a keen interest in better understanding how wildfire affects subsequent fire behavior, as per today's talk, but also how climate shapes fire regime characteristics. He relies heavily on GIS, satellite imagery, and statistical models for his work, but also dabbles in some work on wildlife connectivity. So, with that, I'll turn it over to you, Sean, and see if we can get more of these people on the phone line and find out what happened there.
Okay, great. Thank you all for attending. And so I don't forget at the end, I want to thank the Fire Consortium involved for hosting this, and in particular to Xander and Barb and Vita and Corey. So thank you very much for hosting this webinar. And so today I'm going to be talking about the ability of wildland fire to act as a fuel treatment. And my co-authors are Carol Miller and Lisa Holsinger. We all work for the Aldo Leopold Wilderness Research Institute in Missoula, Montana. And this particular project is funded by the Joint Fire Science Program. And we could think about this title or this topic in another way, or what we actually did. And what we did is we quantified the influence of wildland fire on subsequent fire occurrence, subsequent fire size, and subsequent fire severity. So when we initiated this project,
have a great day.
I don't know if everyone's phone is turned off, by the way. I'm getting some sounds. Okay, but anyway, when we initiated this project, we posited that there were three ways in which fire could act as a fuel treatment. The first is that wildland fire could affect subsequent fire occurrence. And so, for example, in this slide here, this map, we posited that fires are less likely to ignite within the perimeters of previous fires and are more likely to ignite outside of those perimeters. The second way in which wildland fire can act as a fuel treatment is by limiting subsequent fire size. Basically, fire can act as a barrier to fire spread and limit the extent of those subsequent fires. So in this particular map, we see two wildland fires, one from 1985 and one from the year 2000. Along comes the year 2003, and it appears as though that 2003 wildland fire is bumping up on the wildland fire from the year 2000. So it appears as though the fire from the year 2000 is acting as a barrier to the spread of the 2003 fire. So in essence, it's limiting the fire size. This isn't always the case. You can see the 1985 fire down there. The 2003 fire breached the perimeter of that 1985 fire. So the 1985 fire is not necessarily limiting the size of that subsequent fire. And the third way in which wildland fire can act as a fuel treatment is by limiting the fire severity of subsequent fires. So here's an example of a fire that burned in 2004 in the Gila Wilderness. This fire is color-coded to a satellite metric of fire severity called the relativized burn ratio, where cooler colors represent lower fire severity, and the hotter colors, the oranges and reds, represent higher fire severity. When I superimpose the previous fire on there that burned in the year 2000, it's shown by the hash marks there, it appears, at least qualitatively, that areas that are reburning have a lower fire severity compared to areas that are not reburning. At least they're not reburning within our recorded fire history data sets. Obviously, these all areas have burned at some point in history. We just don't know when. So again, to reiterate, we are going to focus on how wildland fire affects subsequent fire occurrence, subsequent fire size, and subsequent fire severity. But after fire, we all know that fuels regrow and biomass reaccumulates. So what we expect is that basically as the fire-free interval increases, the ability of fire to act as a fuel treatment will be diminished. Weather also plays a key role in that there are extreme weather events that will probably diminish the ability of fire to act as a fuel treatment. So for our study, we did our best to incorporate time since fire and weather into our analyses to basically analyze the effect of both time since fire and weather. So we studied these questions in 4 study areas: the Frank Church River of No Return Wilderness in central Idaho, and the Selway Bitterroot Wilderness in Idaho and a little bit in western Montana, and the Crown of the Continent ecosystem, which is comprised of Glacier National Park and the 3 wilderness areas immediately to the south of it, affectionately known as the Bob Marshall Wilderness Complex. And finally, in the Gila and Aldo Leopold wilderness areas down in New Mexico. And why did we focus on wilderness areas or protected areas? There's several reasons. First of all, there are no mechanical fuel treatments or roads in these wilderness areas. There are some roads, of course, in Glacier National Park. But for the most part, most of the areas we analyzed were roadless and didn't experience mechanical fuel treatments. Mechanical fuel treatments obviously would affect fire behavior and effects, so we did not want that confounding influence in our analyses. We wanted purely to look at fire. And roads also act as a barrier to fire spread in some cases, but also facilitate more effective fire suppression. So making sure we didn't have those influences was very important to us. Also, these particular areas have fire use programs. So they've experienced a lot of fire over the last few decades. And what that means is that they do allow some fires to burn under certain conditions. And in all these areas, they still do suppress wildland fires, but they also allow some to burn. So what these areas provide us is basically an adequate sample size in which to analyze these fire-on-fire interactions and feedbacks between past fires and subsequent fires. So I'm first going to tackle the component of the project that looks at fire occurrence, meaning how do wildland fires affect subsequent fire occurrence? So the first thing we did was generate a fire history atlas, which most of you know is basically a GIS file full of polygons that show where the fires burned. This fire atlas includes all fires greater than or equal to 50 acres and covers the years 1972 to 2012. To generate this, we first obtained the base fire atlas from the Monitoring Trends in Burn Severity data set that covers those years 1984 to 2011 and includes only large fires. Large fires, according to MTBS, are fires larger than 1,000 acres. So what we did is we supplemented that MTBS data set by identifying and mapping all fires greater than 50 acres, from the 1972 to 2012 time period. We used satellite data in the whole record of Landsat data, including the multispectral scanner data from the 70s and early 80s. And this was time-consuming and difficult, but we basically had to obtain and download all fire-free, smoke-free, and snow-free satellite images and analyze them for fire. So for these particular study areas and for these particular years, 72 to 2012, these fire atlases are probably the most comprehensive and detailed fire atlases out there. The second key piece of information we needed was to know where the subsequent fires occurred, or where did they ignite? So in the context of our study, it's important to recognize that a fire occurrence is an ignition that resulted in a fire greater than 50 acres. So a burning snag does not count as a fire occurrence in this study, or small fires, less than 50 acres do not count as a fire occurrence. So again, we are analyzing whether past wildland fires are influencing subsequent fire occurrences. So for the fire occurrence data, we used several sources of data. For the years 1992 to 2012, we used a data set from Karen Short, who works at the Missoula Fire Sciences Lab. And for the other years, we used a hodgepodge of different data sources to cover the years 1972 to 2012. And what we did is we evaluated the elapsed time between a wildland fire and that subsequent ignition. And we evaluated the elapsed time for not only real ignitions, but also randomly placed ignitions. And I'll talk more about this as we continue. But basically, what we'd expect is that the elapsed time between a wildland fire and a real ignition is going to be longer than the elapsed time of that between a wildland fire and these randomly placed ignitions. So we would not really expect observed ignitions to fall within fires that are, say, 1 and 2 and 3 and 4 years old. And there's going to be a much higher probability that these random ignitions are going to fall in fires that are, say, 1 and 2 and 3 and 4 years old. So again, we expect longer elapsed time between wildland fire and real ignitions between that of wildland fire and these random ignitions. And we used a statistical analysis called survival analysis, which has been used in fire studies in the past, but is actually very commonly used in medical studies. And in this example here, it quantifies how long a cancer patient survives on a drug treatment compared to a placebo. So on the y-axis, you see this probability of survival. On the x-axis, you see time. And the treatment, you have a higher probability of survival compared to the placebo. And if the probability of survival was not higher than the placebo for this treatment, then that treatment would not be very effective. So that's how they do it. That's one way they study drugs in the medical field. So in our study, though, we're going to look at real ignitions and random ignitions as kind of our analogs to the treatment and the placebo. So again, our expectation is that the elapsed time between fire and real ignitions is longer than the elapsed time between fire and these random ignitions. And if this expectation holds true, we're going to see survival curves that look like this, that look like what you see on the bottom. I do want to note the random ignitions mimicked the observed ignitions in that we used a stratified random sampling design. So for example, say 35% of our observed ignitions fell within a Douglas fir forest type. We ensured that 35% of our random ignitions also fell within a Douglas fir forest type. And this basically prevents random ignitions from falling in land cover classes that do not ignite and do not burn, for example, open water and barren areas. Had we not used this stratified random sampling design, we would have basically overinflated the difference between the survival curves of the real and random ignitions. And again, yeah, we're just basically going to expect a higher probability of survival for the real ignitions compared to the random ignitions. So here are some results for the Frank Church Wilderness area. You can see in red it shows the survival curve for the observed ignitions, and the black line shows the survival curve for the random ignitions. So these obviously look quite different, but these survival curves in of themselves do not tell us two pieces of key information that we were really interested in knowing. We wanted to know, number one, we wanted to know how long does the effect last? Or said another way, how many years does wildland fire prevent the occurrence of subsequent fires? So that's one key piece of information. The other piece of information we wanted to know was basically the magnitude of that influence. For example, is there a 50% reduction in fire occurrences due to the previous fire? Is there a 10% reduction, or is there a 90% reduction? So, a 10% reduction is not, is not that substantial, but a 90% reduction would be like, yes, that's a very large effect. So to get at those two questions, or those two key pieces of information, what we did is we actually divided the slopes of these survival functions for each year. And it's kind of a funky concept, but basically, if you divide the slopes of these survival functions, we generated a metric we're coining the relative ignition ratio. And basically any relative ignition ratio value below 1 indicates that yes, fire is limiting subsequent fire occurrence. Once the relative ignition ratio reaches 1, basically the fire occurrence is just as likely as by chance to fall within previous fire perimeters. So this relative ignition ratio for the Frank Church is basically showing us two good pieces of information. First of all, the ability of fire to limit subsequent fire occurrence lasts 25 years or greater than 25 years in this particular wilderness area. And also the magnitude of that effect, you could see how the relative ignition ratio varies by time since fire, but basically on average somewhere between 0.5 and 0.6. Remember, again, a value of 0.5 would indicate that there's half as many ignitions within previous fire perimeters compared to that expected by chance. So I'm going to show the results for the other study areas now. Here's the Selway Bitterroot Wilderness. And you can see on the left the survival curves are as we'd expect. Again, the relative ignition ratio, however, reaches 1 at 23 years after fire. So basically, the ability of fire to limit subsequent fire occurrence lasts 23 years in the Selway Bitterroot Wilderness. In the Crown of the Continent ecosystem, we could look at this relative ignition ratio and how it varies since fire, and it shows that basically fire will limit subsequent fire occurrence for 21 years. However, the values of the relative ignition ratio are actually quite low for the first, 1 to 20 years after fire. Well below 0.5 for many of those years. And finally, in the Gila and Aldo Leopold wilderness areas, we see that the relative ignition ratio reaches 1 after 8 years. So after 8 years, fire will no longer influence subsequent fire occurrence in the Gila and Aldo Leopold wilderness area. And that is, note that 8 years is obviously much shorter than the other 3 study areas. And that's what we'd expect given the fire regime characteristics of that southwestern study area compared to these other 3 study areas that are in the central and northern Rocky Mountains. So what about extreme weather? I mentioned that we're going to get into weather. So to evaluate weather or weather's influence, what we did is we looked at the Palmer Drought Severity Index. And we compared basically drought years to non-drought years. And so you could call that weather, or you could call it climate variability. It depends what you want to call it. But basically, we called each ignition associated with it, whatever year it occurred in, it was assigned either a drought year if the fire season PDSI was less than -2, and we said it was a non-drought year if the fire season PDSI was greater than -2. So basically what we're doing is we're comparing drought years to non-drought years in this analysis. And I'm just going to show the results for the relative ignition ratio. I'm not going to show the survival curves. But what you see here is that the relative ignition ratio is shown here on the y-axis again, and drought years are shown by the red line, and non-drought years are shown by the blue line. And so again, when the relative ignition ratio is 1, that indicates that wildland fire no longer limits subsequent fire occurrence. So you can see that in the non-drought years, fire does still have a very strong effect on subsequent fire occurrence. and it's weaker in drought years, which is what we'd expect. The Gila and Aldo study area is interesting. It's an interesting comparison because you could look at it and say that in drought years, fire limits subsequent fire occurrence for about 5 or 6 years in these drought or extreme conditions, but that effect will last 14 years in the non-drought years. So the next component of this study is basically looking at fire size. How does wildland fire affect subsequent fire size? We use the same fire atlas that I previously described, which is a reminder, includes all fires greater than 50 acres and covers the years 1972 to 2012. And what we did for this study is we basically identified for each fire perimeter which portions of those perimeters were quote-unquote limiting or not limiting subsequent fire spread. So here's an example from a fire that burned in 2007. You can see there's a subsequent 2008 fire, and everything labeled in blue or shown in blue shows that, yes, it's limiting subsequent fire spread. I do want to say that whether or not it limited or did not limit subsequent fire spread was basically based on a rule set we developed. I don't want to get into the exact rules because it's a little too much information, but basically it involves a bunch of distance thresholds between previous and subsequent fires. But I will say the rule set was consistently applied to all fires and to all study areas. And I'll show you some more examples of how this looks. Here's a 2003 wildland fire that interacted with a 2007 wildland fire, and you can see that based on our rule set anyway, a large portion of the 2003 wildfire did limit the size of that 2007 wildfire. But based on our rule set, there are some areas that are shown in red that did not limit the size of that 2007 fire. Here's another example where we had a wildland fire that burned in the year 2000. It's shown entirely in red because the subsequent fire from 2007 completely ran over that previous wildfire. So none of the perimeter from the year 2000 limited the size of that 2007 wildfire. So here's just kind of many of those examples put together, but just to reiterate, we basically labeled pixels as yes or no, they limited or did not limit subsequent fire spread or subsequent fire size. And what this allowed us to do is use a logistic regression model where limiting is assigned a value of 1 and not limiting is assigned a value of 0, because logistic regression uses a binary response variable. And so using this approach, what we're able to do is look at basically the probability of wildland fire limiting the size of subsequent fire as a function of time since previous fire. And what we would expect is that immediately after the fire, yes, a wildland fire has a very strong effect on subsequent fire size. And then we'd expect that as time since fire increases, that effect is going to decay. And in fact, that is what we see here. The plot on the right shows the model fit, the logistic regression model fit for all the study areas that are color-coded. For example, the Frank Church is in red and the Gila and Aldo is in blue. The y-axis shows the probability of fire limiting the size of subsequent fires. And you can see on the x-axis is time between fires. And what we're kind of arguing here is that once that probability reaches a value of 0.3, that wildland fire no longer limits subsequent fire size or no longer acts as a fire break. And that's admittedly a very arbitrary threshold, but it allows us to compare and contrast study areas. So for example, we could make statements such as fire limits subsequent fire spread for 6 years in the Gila and Aldo study area, but fire will limit subsequent fire spread for about 17 years in the other 3 study areas. And so there's that. Now, what about extreme weather? We want to include extreme weather into this analysis as well. So what we did is we first estimated the day of burning or fire progression for all large fires, those greater than 1,000 acres for the year 2001 to 2012. We did this using MODIS fire detection data and some methods described in a paper published last year in IJWS. But the quick and dirty is that basically for each of the red dots here in this left map, we know the date that the fire was detected. And using the methods in this paper, we were able to basically interpolate between those dots to get a very fine scale and spatially continuous representation of day of burning or fire progression. So once we know what day each pixel burned, it allows us to evaluate weather because we can obtain weather information from nearby weather stations. So what we did is we obtained the daily energy release component, or ERC, from nearby weather stations. And when we do that, we're able to say, for example, if that arrow pops up there, we can say we know what the ERC is when that 2003 wildland fire bumped up against that fire from 2000. And we also know the ERC when this 2003 wildland fire breached the boundary of that 1985 fire. So what this allowed us to do was build a logistic regression model with two covariates. We used time between fires and ERC. And what you see is that, yes, extreme weather does diminish the ability of fire to limit subsequent fire spread. The red is kind of the extreme conditions, the 99th percentile ERC values, whereas the black is the more moderate ERC values, the 50th percentile. And what you see is that basically fire's ability on subsequent fire size is weaker and decays faster and doesn't last as long under these extreme conditions compared to the more moderate conditions. And this pattern is seen in all study areas, as you can see here. And there are some interesting comparisons you can make between the different ERC percentiles. For example, in the Gila and Aldo study area, under extreme conditions, under these 99th percentile ERC conditions, fire limits fire size for only 2 years. But under the more moderate conditions, it lasts 8 years. So under moderate conditions, fire limits fire size for 4 times longer in this particular study area under moderate conditions compared to extreme weather conditions. So from a climate change perspective, obviously this is important, as if we do expect increasing extreme weather or higher ERC values in the future, that fire will make a less effective fire break, I guess, and we'd expect higher rates of burning, which is very consistent with a number of other studies that have been published, basically stating that, yes, with climate change, we're going to get more frequent fire. So the third component of our study is to look at fire severity. And basically how does wildland fire influence subsequent fire severity? We're defining fire severity as the degree of ecological change, and that's measured with Landsat satellite imagery using a pre- and post-fire image, and specifically using the delta normalized burn ratio, or DNBR. And I'm fairly certain that most or all of you have encountered or are aware of this fire severity metric. This DNBR has been shown to strongly correlate with field-based measures of burn severity, and specifically I'm talking about the composite burn index, and I'm going to get back to the composite burn index, and for short that's CBI. I'm going to talk about that a little bit later, so it's important to recognize the strong correlation between DNBR and CBI. And there are many detractors from satellite renditions of fire severity, but the reality is if you want to evaluate fires, many fires over large landscapes, these satellite metrics are pretty much the only way to go at this point in time. So I will say that for this component of the study, we did only look at 2 of those 4 study areas, the Frank Church and the Gila and Aldo study areas. I will also say that we did not use the aforementioned Fire History Atlas. We stuck entirely with MTBS data, the Monitoring Trends in Burn Severity Project's data. That includes all fires larger than 1,000 acres, and at the time this study was conducted from the years 1984 to 2009. And what we did is we basically just compared areas of reburn to areas that have not reburned. And to show an example here, you can see the areas that have reburned would correspond to these areas that, a fire is burning over a previously recorded fire, and areas that did not reburn are burning over a previous fire, but we don't know when that last fire was, so we're just calling it no reburn. So it's rather simple, actually. We just compare the DNBR, or the mean DNBR, in and outside of these reburn areas. And the results I'm going to show are for all the fires within each study area, not just this fire. This fire is just shown as, for illustrative purposes. But we also are going to show a new metric we're coining called the derived CBI, and we'll get to that a little bit more in a moment here. But the results show that in reburn, the DNBR is lower than in no reburn, right? The DNBR has a value of 89 in reburn compared to no reburn has a value of 213. One of the issues with DNBR is there is no ecological context. What does DNBR of 89 really mean? And that's where we introduce this term called the derived CBI, or the derived composite burn index. Because there is a strong relationship between DNBR and CBI, as you can see here, we can basically use the DNBR values and derive the CBI values for those particular DNBR values. So it's commonly accepted in the literature that CBI values below 1.25 are quote-unquote low severity, and values between 1.25 and 2.25 are quote-unquote moderate fire severity. So when we use those thresholds and we used our derived CBI values, what we see is that on average, the CBI values in reburn is quite low, less than 0.5, which corresponds to low severity. And then in contrast, in areas of no reburn, the derived CBI is 1.6, and that corresponds to this quote-unquote moderate burn severity. So yes, in this study area, fire is limiting subsequent fire severity. And we see similar patterns in the Frank Church Wilderness area, where the DNBR is much lower in the reburn compared to the non-reburn. And if we use a plot here on the right to kind of derive the CBI of those DNBR values, what we see is the derived CBI in reburn is 1.1, and again that corresponds to quote-unquote low fire severity. And then in no reburn, the derived CBI is 1.9. That corresponds to moderate fire severity. Now, just to show you just a couple pictures of what these reburns and non-reburns, no reburns look like in these study areas. Here's a couple pictures from the Gila and Aldo, actually from the Gila Wilderness. And then here's a couple pictures from the, it's actually not from the Frank Church Wilderness. These pictures are from the Bob Marshall Wilderness. So that's what kind of the reburn versus no reburn look like out in the field, or one example of what it looked like. And so we also wanted to look at the influence of time since fire. And I will apologize that we did not evaluate the influence of weather for this component. But we did evaluate the influence of time since fire. So what we did is we basically modeled DNBR as a function of time since previous fire. And we'd expect increasing DNBR as time increases. So for this little sub-analysis, we could only look at areas that reburned, because in areas that did not reburn, we do not know the time since previous fire. Again, obviously it burnt at some point in history. We just don't know how long it was. So we stuck with these areas that only reburned, and we know the exact interval between, or the exact time since the last fire. And this plot is a little funky, but it does show that, yes, as expected, reburn DNBR does increase with time since fire. The red line shows the model fit. The DNBR, or the reburn DNBR, is shown on the y-axis here, and the dots show the data. The size of the dots show the relative amount of data for each of those years since previous fire. We don't have equal representation from each year since previous fire. And so the dashed line, however, represents the DNBR of all pixels that did not reburn. And what that means is that basically as long as this red line and these dots are below that dashed line, yes, fire is limiting subsequent fire severity. So what you see is this red line is well below the dashed line all the way out to more than 20 years since fire. So what we can infer is that the effect of the previous fire on subsequent fire severity lasts more than 20 years. We don't know how many more than 20 years because we don't have the data. We don't have the satellite record to evaluate that. But for what we have, this is what we can show. This component of the study has been published in Ecosystem. So if you want to know more of the ins and outs of it, you can check out that bad boy. So to kind of wrap this up, yes, wildland fire does act as a fuel treatment, and it limits the occurrence of subsequent fire, and that effect lasts 8 to more than 25 years, depending on the study area. Yes, fire does limit subsequent fire size, and that it lasts 6 to 18 years, and that depends on the study area. And yes, wildland fire limits the severity of subsequent fire. That effect lasts than 20 years, potentially much longer, but we don't really know because we don't have the data. And then basically, I just want to kind of emphasize here that there are long-term benefits of wildland fires, and one of those long-term benefits is that, yes, they act as a fuel treatment. So when deciding how to best manage a fire, it's important to consider these long-term benefits and not just the short-term, quote-unquote, costs of fire. But it's also important to note that, yes, these effects do weaken over time, and that the longer the fire-free interval, the less likely wildland fire will act as a fuel treatment. And it's also important to note that under extreme weather conditions that fire's ability to act as a fuel treatment is reduced. And from a real big picture perspective, I just want to point out that many landscapes in the western U.S. and elsewhere, Alaska as well, have experienced a lot of fire in recent decades. And because wildland fire does act as a fuel treatment, this might perhaps provide an opportunity to reintroduce natural fire, knowing that fire severity, size, and fire occurrences will likely be limited by these past fires. And I'll kind of close with this statement here, in that in some situations, suppressing fires actually may result in a lost opportunity. There are some situations, for example, under moderate weather conditions and when there's other or past fires in the vicinity that will act as a fuel treatment. If these are the cases, perhaps suppressing all these fires is a lost opportunity, and just wanted to mention that. And I will close there. And again, my co-authors are Carol Miller and Lisa Holsinger, and various other folks have contributed to this project, including Zach Holden, Karen Nelson, Scott Baggett, and Ben Bird. And I want to thank the Joint Fire Science Program for funding this project. So I'll end there with questions, but I also just want to mention that today, January 21st, in case you didn't know, is National Hugging Day. So, give everyone a hug and check out nationalhuggingday.com. Okay?
Well, thanks, Sean. And some people may need a hug after the confusion we had over the phone numbers. So I want to apologize to everybody. I guess one of the emails that went out after people registered included a number to a hospital somewhere. So that was our fault, and I apologize for that. But I hope everybody did get on the line, because, Sean, that was an excellent presentation. And really, as someone who's done a fair amount of GIS work myself, I'm blown away by the effort and results you guys got. So thanks so much for the presentation. And we do have a number of good questions in here, and I will try to pull them out of the chat window and reiterate them for those people who don't see them as easily. First question comes in from Gloria Edwards, and she was wondering about the ability or utility of including some tree ring fire history in addition to the satellite histories that you had, I think preliminary, mainly for that first portion of the study you talked about.
For fire occurrences.
Yes, yeah, for building that fire atlas.
Right. Well, that is certainly possible. It's my understanding that there's a lot of tree ring studies out there, but they would not be very comprehensive, say, pre-1972 for our particular study area. I mean, we'd have to initiate our own probably tree ring study to do that, and that would involve much more work than using these satellite data. So while it is a possibility, given the data that's already out there, we'd have to basically add that ourselves, and that would be pretty difficult.
Okay, so basically you didn't have the existing tree ring record, so yeah, you'd have to recollect it. Then Matt Thompson asks a question about maybe you can talk a little bit more about some of the maxima in the curves for the Frank Church and other areas around those 10, 15-year window. And I think you kind of hit on this a little bit, but maybe part of what Matt's getting at is sort of natural fire return intervals for some of those forest types.
Perhaps. Those humps were actually very interesting. So those humps were in the Frank Church Wilderness area and the Selway Bitterroot Wilderness area. And I'm not sure exactly what's going on. I'd be curious to hear what any of you think about that. But our current line of thinking, and this is just a theory, is that those two areas do experience a lot of stand replacing fire, and so perhaps after stand replacing fire, the probability of subsequent fire ignitions increases as fine fuels, twigs and branches and needles fall off of trees. But then maybe after, say, 12 to 13 or 14 years, there's crown closure from the small regenerating trees, which increases fuel moisture, and maybe that then decreases the probability of ignition. So that's one theory, and if anyone else has any other ideas why that might be, I would be all ears.
Great, interesting. Yeah, could be a future research there. Christopher asks about the limits to fire size, and oh wait, I skipped a question, I'm sorry. Did you factor in, when you were looking at the limits, limiting old fires, limiting new fires, did you factor in topography at all in that effort?
The short answer is no. The way the study was designed made it very difficult to factor in topography. I will say that we are initiating a new study here, and we are specifically designing the study so we can evaluate the effect of topography and maybe interactive effects between topography and past fires.
Great, okay. And then again on the limits to fire size, did you look at the, with Christopher O'Connor asks about stratifying by forest type and the potential changes in forest type affecting those changes in fire. Is that something you might look at or have looked at?
It is something that we did not look at. It is something I am interested in looking at for sure, but we did not look at it for this particular project. And
let's see, going back through the questions here. would you mind talking a little bit more about what you classify as drought and how drought was built into the statistical work?
Right. So drought, quote unquote drought, is when the fire season PDSI or Palmer Drought Severity Index was less than -2. And so basically, because we know the year of each ignition, we don't know the date of each ignition, but we know the year. So we just assume that that ignition occurred during the fire season. So we assigned each of those ignitions a PDSI value, and then we could just basically say, yes, it's drought, or it's non-drought. And then using survival analysis, we basically essentially built two survival curves, one for drought, one for non-drought. One thing I forgot to mention on that slide is that the crown of the continent ecosystem was not shown there. And the reason the crown of the continent ecosystem was not shown there is because the statistical significance between the survival curves of drought and non-drought, it was not statistically significantly different. And what that means is not that there's no difference, but there's a little bit more of a data limitation in that study area because there's less fire. So I hope that answered the question.
Yeah, no, I think that clarifies how you dealt with drought. And then Robert asked a question about thinking about that reburn section of the study, the influence of burn severity of the initial burn on the reburn. Was that something you built in?
It was built in. I didn't show the results here, but if you look at the paper, one of the figures in there does show that as the severity of the initial fire increases, the severity of the subsequent fire also increases. And that particular phenomenon is actually observed in a lot of other studies that have looked at fire severity using these severity indices. So I forget them all, but I know there are other studies that also found that same relationship.
Interesting. Sitting here near the Las Conchas burn, that's particularly relevant to those of us in New Mexico. Let's see, there was another question about the real versus random ignitions. I wonder if you could sort of reiterate how you described the modeled random ignitions and their role in your study.
Right. So random ignitions were, so real ignitions, we know where they ignited, and we could evaluate the elapsed time between fires and these real ignitions. The random ignitions were just kind of thrown at the landscape randomly, but there was that stratified random design that I did talk about earlier. But so you just kind of, randomly throw these ignitions out there with certain constraints, and then you expect that the elapsed time between wildland fire and these random ignitions is going to be much less than the elapsed time between the wildland fires and the real ignitions. Hopefully that answers the question.
Yeah, oh, that's great. And then the next question in our lineup here from Hardy sort of gets back at something you were just talking a minute ago about, and he or she asks, are there negative potential impacts of introducing fires into forest landscapes where reburn becomes so frequent that forests are burnt off before maturity? Can that lead to regime change? So that might be related to that high severity on high severity you were just talking about.
Right. Well, yeah, that's certainly the case. This idea of reburn and using satellite metrics to characterize it is that's kind of an initial first step. I know that there are multiple people out there that have initiated field work to look at this, and certainly short interval fires or short interval high severity fires in particular could cause regime changes because feed sources are consumed. So that is definitely a possibility. Great.
And then the next question is whether you think the variability in the regions between the time to become more receptive to a second fire is a result of weather or post-fire successional types in the study area.
So I don't quite understand the question, but I think it has something to do with the study areas have a lot of variability within them. And so basically, how does that variability influence the results here? Is that right?
And I think she's particularly hinting at the difference between the Gila, Aldo, Leopold wilderness and the ones farther north, where you have some real regional differences that you touched on a little bit. But obviously, part of those regional differences is the weather, and the fire weather being more frequent down here than up there. But it also, you have different forest types, so I guess both those are at play.
Right, yes, they definitely are. I will say that, the actual amount of reburn as we move north through these study areas decreases dramatically. So for example, in the Gila and Aldo study area, something like, and I don't know the exact number, so please don't quote me, but something around 30 to 60% of the fires are actually reburning past fires. And in the Frank Church, that number is 15%. So 15% are reburning past fires. And then in the Selway Bitterroot and the Frank Church, in the Selway Bitterroot and the Cranot-Continent ecosystem, as of 2009 anyway, that percentage was less than 3. So less than 3% was actually reburning. So there are definitely ecoregional differences here that I saw. Great.
And Will had another follow-up question thinking about this reburn and vegetation types. Let's see, I guess I'll just read the question. Maybe that's the best way to do it. Does the analysis assume veg types being the same post-initial burn? What about the question of regime changes? And he provides the example of a ponderosa pine forest burning and then coming back being oak-dominated, and then it would be more likely to reburn quickly. So is that something you could build into your analysis, or is that sort of opaque to the satellite imagery?
It's definitely opaque to the satellite imagery. That would definitely involve some field work, and that's what other people are starting to do, is to get out there in the field and to look at, these post-fire successional pathways, and then, whether or not it reburns, and then what happens again. But from this study, this was kind of, as I view it, kind of like an initial first look at this question, using satellite imagery, and there's lots of limitations, and field work will hopefully elucidate some of the other issues going on.
Great. And I should note that we've come to an hour on this talk, and I want to say I think you did a great job. You've gotten lots of kudos here in the chat window. For those of you who have to drop off, that's fine. We will have a recording available soon in case you missed early portions of it due to some phone problems. But if you can stick around, I think we may be able to get Sean to answer a couple more questions. And so with that in mind, let's go to this question. Gloria asks if you got any interesting comments or feedback from firefighters. I was sort of more people on the line, if they had seen anything different, or did that come up at all in your work?
No, it has not. I generally have not presented to firefighters. I did present to the regional FMOs and AFMOs, and they didn't say anything that was, I don't know. They didn't have too many comments.
Okay. Let's see. And so thank you, Carol, for helping to answer Jennifer's question about the random ignitions. I think that's maybe dealt with. And Matt Thompson asks about the photo. I think he's wondering about the photo up on the screen. Was that taken in November?
It actually asked if it was taken in Movember, and it was not. It was actually taken in August. Matt, thank you for the question.
All right. So I'm hesitant to unmute the line. I know we have a bunch of people still participating. So if there are any last questions, please feel free to type them in the chat window. And maybe while we're waiting to see if there are any last questions, I wonder if you might mention, Sean, some of the next things that you're working on, things that might be in progress that we can look forward to.
Sure. I actually have a couple more components of this study I would like to work on, and that is depending on whether or not I can get funding to work on those components. Another thing I am working on is definitely the relationships between fire and climate, and not only just area burned or fire frequency, but also looking at fire severity. And so if I could build strong relationships between fire severity and fire frequency and climate, it kind of gives us a better picture of the fire regime in of itself, because there's been many studies looking at, say, area burned in relation to climate, but not many looking at fire severity. So I'm actively working on that.
Great. Great. Well, I have one other question, and I was wondering whether, obviously you're aware of a lot of the other research going on in more managed landscapes, and I wondered if you had any feelings about how some of your findings connect with other studies, maybe using some of the same MTBS data, like was it Cochrane, who had a recent study looking at fuel treatments and fire size, and whether there were any things in sort of differences between those using wildfire as a treatment and regular fuels treatments that you notice particularly, or maybe that's not a area you focus on.
Well, because I focus mostly on wilderness, I do not look at a lot of the other traditional fuels treatments, prescribed fire and mechanical fuels treatments. But there's been a lot of work looking at fire severity and its relationship to past treatments, and it's possible. I think the new report that came out by Camille Rumen-Stevens, I'm going to butcher your name, I'm sorry, and also Penny Morgan might talk about some of that in relation to how fire size and fire occurrence are affected by these other treatments. I'm not aware of anything that looks at that.
Great. Well, any last comments, and then maybe we'll let you go. Well, thanks again, Sean. And as I said, we'll have a recording of this available, and I look forward to hearing about your future work.
Great. Thanks, everyone, for showing up.
Okay, great. Thank you. Bye.
Bye.